Welcome to the first set of slides for Math 260, Linear Systems and Matrices. Because the word matrices is in the title of the class, that's the first thing we're going to take a look at. As you go through these slides through the course, I'm going to presume you will make judicious use of your pause and rewind buttons to pick up on things that you might have missed. You have the technology in your hands, so make sure that you're using it to the best way available. In these first slides, we're just going to look at the basics of matrices, what the heck they are, what's in them, what kinds are they, and we will look at how something you've already heard of before, vectors, are just one particular example of this broader concept of matrices. Overall, matrices are just boxes of stuff. Generally, in math classes, we will be looking at boxes of numbers, perhaps boxes of formulas, boxes of variables or constants, or any mix of the above. So all the things you see on the screen here are all matrices. They're organized by rows and columns, and you don't have to have the same number of rows and columns, although life tends to be easier when you do in a lot of cases. One of the big examples we'll get to as this course gets up and rolling is linking solving systems of linear equations, which I'm sure you've done before, to the idea of matrices, and matrix engines will make that process much simpler and make the problems easier to analyze. So some of the particulars of matrices: a matrix can be in a different configuration from a different matrix in terms of rows and columns, and so that's what we start with in terms of their descriptors. So the order of a matrix, you say it's something like a 3 by 3 or a 2 by 4 or a 1 by 6 or anything like that, where the first number in that descriptor is the number of rows in the matrix and the second number is the number of columns. So here's two matrices on the screen now. The first one on the left has 2 rows and 3 columns, and so it's a 2 by 3 matrix. The second one has 3 rows and 2 columns, so it is a 3 by 2 matrix. Once we dig into the matrix, we have to be able to pinpoint specific entries, and so we just locate them by their row and column. Will be like a little matrix Google Maps or something. So the red entry, the number 1 in this particular matrix, is in the first row and first column. We count from the upper left, and so that is entry number M11. For entry number M21, well, that's the entry in the second row and the first column, and so that will be the blue -1. M22 is the entry in the second row and second column. Again, counting from the upper left, that's the 0, and so on. Okay, terminology. Sometimes we're going to talk about a square matrix. That term is fairly self-explanatory, so without any further introduction to it, here's 3 matrices on the screen. Can you tell which one of the 3 is not a square matrix? And it is the one in the lower left-hand corner. The rest of them have the same number of rows and columns. They are square. The one on the lower left has 3 rows but 2 columns, and so it is not square. A diagonal matrix is another special kind of matrix, and these are matrices that have non-zero entries only on the forward diagonal. That means upper left to lower right. So non-zero entries, or maybe even 0 entries on the main diagonal, but zeros everywhere else. So one of these on the screen is not a diagonal matrix. The first one is in the upper left-hand corner. The 2 and the 5 are on the diagonal. They're non-zero. That's great. Off the diagonal, zeros everywhere else. The matrix in the upper right has 3 variable expressions down the main diagonal. Zeros everywhere else. That's great. The lower left matrix has zeros off of the diagonal everywhere. That's great. It happens to have zeros on the diagonal too. That's fine, but it's still a diagonal matrix. The fourth one is not a diagonal matrix. It does have zeros all the way down the main diagonal, but it has some non-zero entries off the diagonal, and that spoils it. The identity matrix is a matrix that's going to end up playing the role of the number 1, except in matrix context, and we'll see why later on, but here's how you recognize it. It's a diagonal matrix, and more particularly, all of the diagonal entries are just 1s. So here is a 2 by 2 and a 3 by 3 identity matrix. I bet you could write down what the 4 by 4 identity matrix looks like for yourself. Symmetric matrices. Matrices that are mirror images across the diagonal from the lower left to the upper right. One of these is not a symmetric matrix. Which one is it? It's the one in the lower right-hand corner. The first 3 whatever is going on the diagonal is going on the diagonal, and that's fine. But off the diagonal, the other three matrices, upper left, upper right, and lower left, have mirror-like images or mirror-like entries below to above the diagonal. So particularly, say, down here in the lower left-hand corner, you see the mirror image A's, the mirror image B's, the mirror image C's. That is a symmetric matrix. The lower right-hand matrix is not symmetric. And finally, vectors. Vectors are just matrices. They're matrices that happen to have only one row or one column. So each of these is a vector. It's either got only a single row or a single column, and we can then therefore describe their sizes as a vector or as a matrix. The first one, the A1b, looks to me like one row but three columns, and so it's a 1 by 3 matrix. It's a vector with three entries. The upper right one has XYZ from top to bottom. That looks like it has 3 rows but one column, so that's a 3 by 1 matrix or vector. The lower left is just a single one. That's 1 by 1. One row, one column. And then the fourth one is 1 row, 4 columns. And so there you can see all the sizing that goes along with these vectors. Watch this, listen to it again if you need to recapture some of those terminologies, and we will get some of them into use in the next set of slides, which would be, cleverly, Unit 1, Part B.